discussion of logarithms, and we'll pass back through the introduction material that I closed the last session with. And we will be talking about properties of logarithms today and their graphs. Okay, now based on the introductory remarks in the last session, if somebody came up to you and said, "What is a logarithm?" what would you tell them? So go see Robert.
Talk to somebody besides me.
Yeah. Anybody have an idea? What would you say if somebody came up and Max?
A number to the power of x.
That's getting in the ballpark, but not quite right. Anybody else want to offer an idea?
Is it the opposite of an exponential function?
Well, we don't call it opposite.
Inverse.
We call it an inverse. Okay, so that's important for you to remember. We've learned how to form inverses, and how do you form inverses? How do you form an inverse of anything?
X and Y.
You interchange the inputs and outputs. In other words, in algebra, typically with x and y for your input and outputs, you reverse those, and then you solve for y. So if you have an exponential, a logarithm could be thought of as the inverse of an exponential. Is an inverse, and it's actually a function. It's an inverse function. Logarithm is an inverse function of an exponential.
And the exponential doesn't have to be a function.
Well, hold it. Think about what we've talked about on exponentials. Think about their graphs. Think about exponentials graphs. Not polynomials, but exponentials. Exponentials look like either a growth exponential, that's called a growth exponential, or a decay exponential. They don't come back up, they go down towards an asymptote. That would be a decay exponential, falling as you move through the domain. A growth exponential would be growing as you move through the domain. So if you take one of those, either one of those, and notice either one passes a horizontal line test. Each have a domain and a range. If you form the inverse, since these pass a horizontal line test, their inverse would then pass a vertical line test, which means that that inverse will be a function. So here's the idea related to this sort of way of explaining to someone what a logarithm is. If you start with an exponential, say like this, then you interchange your x and your y, and you're going to get a graph that's going to look like this. So here's the exponential, and here's the logarithm. And they will have symmetry around the y equals x line because you're forming the inverse. As I said a moment ago, this passes a horizontal line test. We call that 1-to-1. 1-to-1, passing a horizontal line test. Then the inverse of it passes a vertical line test. Another thing is the domain on the exponential becomes the range on the logarithm. So the domain here becomes the range over here, and the range on the exponential becomes the domain of the logarithm. It's that simple. You just need to remember it. And these little pictures, this pair of pictures right here gives you this thinking. It sort of graphically explains this thinking. And this is a strange word, as I mentioned in the last session. It's a strange word made up of derivatives, I believe, from Latin and Greek. Logo or rhythmos or something like that. I don't speak those languages. But the people that invented these hundreds of years ago did. There is another way that you could explain to somebody what a logarithm is. You could say that the logarithm is just an exponent. Let's go over here. A logarithm is just an exponent. Now, what does that mean? So here's what we did. If we started, give me a base. Give me a base for an exponential. 5. Okay, so if we have an exponential expression, like Todd suggested, a base 5 exponential, this thing graphically would grow as a multiple of 5, and it would be pretty steep as it moves out to the right. And it has what y-intercept here? 0, 1, Jerome, right. 0, 1. When you come over to 1, how tall is it? 5. Everybody agree with what Jerome's suggesting? Okay, you're at 5. When you go over to 2, you're up to 5 times 5, or 5 squared. So as I've said repeatedly, an exponential function grows as you move through the domain. It grows as a multiple of the base. It grows as a multiple of the base. Okay, now, how do you form a logarithm? We just talked about it. How do you form a logarithm?
Switch the y and the x.
You interchange the x and the y, and we did this in last session. So we have 5 raised to the y power equals x. So look up here. A logarithm is just an exponent. A logarithm is just an exponent. Well, the mathematicians decided to write this as y equals the logarithm. In other words, you can think of this as an exponent. Base 5, I have to put a little subscript there, of x. So these two expressions right here and here are the same. These expressions are the same. In other words, the exponent, when you see a logarithm, folks, you can substitute mentally, or say it out loud if you wish. You can say exponent. What's the exponent of 5 that gives you x? Look at this right here. What's the exponent of 5 that gives you x? Okay? So that's a handy thing for you to help you. The sketch of this relationship you see right here is going to be what I just said on the previous board. It's going to look like this, going through what important point? 1, 0. And what would be another very important point?
5.
If you go out to the base value, out here to 5, this thing's going to be up at a height of 1. Just like up here, if you went over in the domain to an input of 1, you're going to have an output of 5. So that 0.15 becomes 5, 1. So let's practice. Let's practice a couple logarithms, and why don't we stick with what Todd had suggested, base 5. So here's a question. Log base 5 of 1. What's that equal to? So what you want to say to yourself is, what's the exponent of 5 that gives you 1? Logarithm is just an exponent. What's the exponent of 5 that gives you 1? Think about it. Jennifer?
0.
0. Perfect. So log base 5 of 1 equals 0. What's the exponent of 5 that gives you 1? 5 to the 0 gives you 1. What would be another way of writing this first question mark right here, this equation right here, and I'll keep the symbol for question mark in here. What would be another way of writing this? 5 to the unknown power, the question mark, equals 1. And Jennifer answered that, has to be a 0. This statement and this statement are identical. These two statements are identical. And that's the same thing that is being stated over here in general. 5 to the y equals x, or y equals log base 5 of x. So there's some new vocabulary here. One new word is all. And the fact that you're already familiar with domain and range, and the key to understanding this is having an understanding of the exponentials. And if you have an understanding of the exponentials, all you do is interchange the inputs and outputs and then solve this thing for y. Y is equal to the log base 5 of x. Let's try a couple more. Let's stick with this base 5 for a second. Oh, one more question. Where is this information on this picture? Look right here, folks. This is an equation, isn't it? This is a function. It's passes a vertical line test. And here's the equation for it. Okay. Here's the equation for this graph. Where is this information right here on this picture? What's the input? What's the input? 1. So you go over to 1, and the output value is 0. This is your x-intercept of this logarithm. This is the x-intercept of the logarithm. These take some practice. Just like everything, as you learn something new, it takes repeated practice to become proficient with it. Here's another question. Log base 5 of 5 equals what? Here's what I want you to think of mentally. What do you think the answer is, Mac? 1. 1. Okay, in other words, what's the exponent? I'm trying to get you in the habit. When you see the word logarithm, think exponent. What's the exponent of 5 that gives you 5? As Max said, it's 1. Okay? The answer here, log base 5 of 5 is 1. What if it was a different logarithm? What if it was a log base 10? Log base 10 of 10 would be 1. Log base 2 of 2 would be 1. And where are you on the graph of the logarithm? Where are you on the graph to illustrate that information? Log base 5 of 5 is 1. The input is 5. The output is 1. That would be this location right here, wouldn't it? Your input is 5, and your output is 1. So for other base logarithms, like 10, like 2, etc., you have to go over in the domain to the basis value. You have to go over in the domain to the basis value to find a height of 1. So if I was dealing with a log base 10, which is called a common logarithm, and I'll give you more detail on that in a second, if I went out here to 10, I would be up at this same height 1 if I was on a logarithm base 10 graph. This would be a log base 10 of x graph right there, and that would be up at 1. So again, it'd be out here at 10, I'd be up at a value of 1. Okay. If you can keep those things in your head, these things will always be 1. What I mentioned in words a moment ago is log base 10 of 10 is 1. Log base 2 of 2 is 1. The equivalent statements shown here is that the exponent here is 1, isn't it? So you see these logs here? The exponent is 1. the exponent is 1, the exponent is 1. The base is shown right here as a subscript. So this says 5 to the 1 equals 5. 10 to the 1, the exponent is 1. 10 to the 1 is 10. 2 to the 1 is 2. And those are just points on the graph. You have to go out to the basis value to be up at a height of 1. So I'm trying to make an algebraic connection for you and a graphical connection. Let me see you folks do one now.